All right, let's look at this problem called frogs and jumps. So what's given in this problem? There are ant frogs at one end of the pond and they all want to reach the other end of the pond. The pond has some leaves in a straight line. Each frog is a strand that tells exactly how many leaves it can jump. So for example, a frog which has strength 2 will visit the leaves 2, 4, 6, etc. while crossing the pond. So we are given the frogs, the number of leaves and strength of each frog. We have to find out how many leaves which are not visited at all. Let's look at this example 3, 4, and 3, 2, 4. So let's maybe look at it on a whiteboard. All right. So we are given frogs 3 of strands 3, 2, and 4, and leaves are 4. So let's say they are indexed from 1 to 4. So 3 will obviously visit just 3, I guess. 2 will visit 2 and 4. 4 will visit 4. One thing to note is that whatever 4 visits will already be visited by 2. Can we optimize that? We have to think about it, right? So that's one approach. Let's look at another example to just clarify it better. So another example, frogs equals to 3. Their strands are 1, 3, and 5, and leaves are 6. So they are numbered from, let's say, indexed from 1 to 6. All right, so 1 will cover everything, right? 1, 2, 3, 4, 5, 6. 3 will cover 3 and 6, and 5 will visit just 5. Now, another thing, 1 covered all the leaves. So for 3 and 5, you didn't need to traverse this. You didn't need this. Let's look at another example to sort of harp on this idea. Let's say uh, frogs. We have of strength 4, 4, 2, 2, 2, 4, 4, 8, 8, 10, 20. And let's say there are 20 leaves, right? So here this 4 will traverse how many leaves? 5. This 4 will go to 5 leaves. This 2 will go to 10 leaves. This will go to 10 leaves. This will go to 10 leaves. This will go to 5 leaves. This frog will go through 5 leaves. This will go to 8 and 16. So 2 leaves, 2 leaves. 10 will go to 10 and 20 leaves. 20 will go to 1 leaves. And all of these with our logic. That can be one approach for the logic. But you see, whatever this 2 covers, okay, whatever this 2 covers will be covered by all of these frogs. And so all of this can be avoided. So let's build that logic. So that logic is first leaf that a frog visits. See, important point is the first leaf. The first leaf that a frog visits, what if it's already visited? How is that possible? See, the point is first leaf. So let's say there is 6 and then 2. So 6 visits 6. 2 also visits 6, but 6 is not the first of the 2 visits. 2 visits 2, 4, 6, right? So I'm talking about the first leaf. So first leaf that a frog visits, what if it's already visited? Only possible if it's visited by a frog of equal strength or a strength which is a factor of frog's strength, right? This, like in this case, this 2 was a factor of 4, 8, 10, and 20. So the idea is whatever these will visit, these have already visited. So in that case, no analysis is needed. That is what I want to try to harp up to sort of improve the time complexity. So let's build a logic based on this idea. All right. So let's try and code here. So let's maintain a list of visited leaves. So let's maintain using a Boolean array. Visited equals to Boolean. We are indexing from one, so that's why we'll make the array size one extra. And let's also maintain total visited nodes. So visited leaves or just visited count. Initialize it to 0. Now let's go through each frog's strength. So for each frog's strength, let's which is the first leaf that will visit, whatever its strength, right? So strength. Now if this leaf is less than or equal to leaves, then only it's like within the leaves. And if it's the first, if leaf is not if and if this leaf is the first leaf, right? So if not visited, because if it's visited, then we don't have to handle this frog at all. That's the optimization that we are sort of dealing with. It's not visited frog. Then let's do this. While leaf is less than or equal to leaves, uh, then we do if not visited leaf, then we do visited of leaf equals to true visited count plus plus. And then we move on to the next leaf. So leaf plus equals to strength. And that's where this while loop will help. And at the end, we'll do return total leaves is leaves minus visited count. That will be the unvisited leaves. All right, so let's compile and run. All right, let's submit. And all the test cases pass. Now the interesting bit to note is if you don't add this optimization and just try and visit all the leaves that a frog can visit, then it will give a TLE error for higher complications, for like large test cases. So this is the optimization where we try and minimize the number of leaves that we sort of walk through for each frog. And that's the optimization that handle that. All right.